So, we have seen the utility of Maxwell's relations, we have seen the utility of Jacobians, and we have seen how to manipulate partial derivatives. We want to carry forward that same discussion now and explicitly, or rather illustrate how to tackle thermodynamic systems or thermodynamic processes. So typically, in thermodynamics, as we have seen, that one deals with processes, and one often will encounter partial derivatives. This is inevitable in thermodynamics. For example, in an experiment, let's say you have a single component system. We'll say a hydrostatic system only. That's the easiest, or that's the best example that we can have. Here, n, the particle number, is fixed. Right? Now suppose you keep the volume fixed, but change the pressure. And you want to find out how much change in the temperature there can be, right? So what I'm required to find out is change in temperature. See, all of these quantities are experimentally measurable quantities, and which means accessible experimentally. So I want to find out dt. So one can imagine that I have taken the system from A to B, let's say, in a quasi-static way, where I've kept the volume fixed, but I've changed the pressure. So I want to figure out how much change in the temperature there is. For this, I will imagine first an infinitesimal step I have taken on this path from going from A to B, and I want to change this incremental change, infinitesimal change dt, and that for me is going to be del T del P, because I'm changing the pressure but keeping the volume and particle number fixed, times dP. One can ask, how much internal energy is going to change? What would be the entropy change in such a case? So on and so forth. Your volume and particle number is fixed. So you see, all of this you can very easily understand if you have a grip over manipulating partial derivatives. They're inevitable in thermodynamics. Absolutely inevitable, right? So what we want to do here is we want to give you some examples, some illustrative examples. Always remember, where one can see how to do these things. Always remember the relations that we typically use if z is held constant is 1 over del y del x z is. This is your reciprocal relation. And then you have del x del y z constant, del y del z x constant, del z del x y constant is -1. This is what is called cyclic relation. And finally, if you have del x del y z constant, and then you have del y del u z constant by chain of, this is z constant. This is chain rule of differentiation applied to partial derivatives. Plus, what is going to come to our rescue is called Maxwell's relation. Right? Now first, so let's start. So for example, if I'm given for a hydrostatic system, I know the information about T and P. So for example, it can be keeping T fixed, I change pressure. It can be T and V, once again keeping T fixed, I change volume, and here also keeping P fixed, I change volume, I change temperature, keeping V fixed, I change temperature. So several of these situations, it can also be a function of P and V, right? Let's take one of these. See, I can write down the entropy now as a function of T and P, because this is the information that is given to me. So it follows ds is del S del T pressure constant, dt plus del S del P temperature constant, dP, correct? And therefore TdS is equal to T del S del T pressure constant dt plus T del S del P temperature constant dP. Now I have to figure out how to evaluate this. So one possible way of clearly evaluating this would be to write down del S del P temperature constant, del P del T entropy constant, and then I have del T del S pressure constant as -1, correct? I can also try to figure out, and then once again here I have to figure out what is del P del T entropy constant. I can also try to see if there is a Maxwell relation corresponding to this. So if I look at the structure of this derivative, then I have del S del P temperature constant. So I have S dt, and the derivative is with respect to a pressure. So therefore I have dP, V dP. So I have to figure out a combination free energy whose differential has this combination. If you look at U minus Ts plus PV, then dG is du minus dds plus pdv. N is held fixed, so we will not worry about N. Minus sdt plus vdp. This by first law is 0, so minus sdt plus vdp. Therefore, del S del P temperature constant, del S del P temperature is constant, is minus del V del T pressure constant. So your TdS is T del S del T pressure constant minus T del V del T pressure constant dP, correct? So one can divide by volume here and bring a volume on top to give you Cp, sorry, there is a dt here. T del S del T is Cp dt minus T V alpha P dP. So your first law completely written down in terms of material parameters. If you know the temperature dependence of specific liquid and the pressure dependence of expansion coefficient, then you know the answer. Now I am asking you that if you want to measure, for example, for this particular case, when s is a function of t, ds, change in entropy, is del s del p. Let's say if dt is fixed, isothermal process, it is just del s del p, temperature constant dp, which is minus tv alpha p dp. Simple. The t is going to go away here because tt cancels on both sides. If you want to say that, look, I have kept my pressure fixed, I want to measure the change in entropy if my temperature doubles as it goes from state A to state B, then the answer is Cp by T dt. That's it, because you have set dp equal to 0. Correct? The more general, if you allow for both pressure and temperature, this is going to be the case. U, if I want to measure du, then it is going to be del u del p. So du is TdS plus PdV, but there is no volume here. So we will simply write down del u del T, pressure constant dt, plus del u del V, del u del P, temperature constant dP. And again here one has to figure out what is going to be del u del P, temperature constant. So let's see. I have TdS is equal to du plus PdV. Correct? So I want to figure out del u del T, pressure constant. Del u del T pressure constant is T del S del T, pressure constant, plus P del V del T, pressure constant. Sorry, it's minus. This goes over here, minus. But T del S del T is pressure constant is Cp minus P V alpha P. Similarly, del u del P, temperature constant, is T del S del P, temperature constant, minus P del V del P, temperature constant. Again, I know what del S del P temperature constant is. This is just going to be minus TV alpha P minus plus PV kappa T. So once you know both of this, you can clearly replenish them over here to figure out the change in temperature, right? So if you say, look, I want to keep the pressure fixed, then du is del u del T, and I have changed the temperature dt, which here is this relation will be used. If you want to say, look, I have kept the temperature fixed, I want to measure the change in the energy as the pressure is doubled, you are going to use this. These relations are only with respect to your response functions, P, kappa T, alpha P. They are not specific for any system, right? What about the second case? In the second case that we discussed, or that we started off discussing, was T and V. Here again, you can write down S as a function of T and V, and ds is del S del T, volume constant dt, plus del S del V, temperature constant dV. This part is very easy. This is the part which is very easy. This is CV by T. It's this part that we have to figure out. So now again I look at the structure of this relation and I see S and V. Let's see if I can figure out a Maxwell's relation. So this means I have S dt and P dV. Correct? So S dt and P dV, the combination appears for Helmholtz free energy. dF is d of u minus ds. Again, n is always held fixed here, so we will not worry about that. Du minus dds minus s dt, which is minus s dt, and du minus dds is essentially minus p dv, because your first law is du is dds is du plus dv. Mu dn dn is 0, therefore we don't worry about it, and therefore it follows that del S del V temperature constant is del P del T volume constant. Very nice. So this one now I have del P del T volume constant. It is still not yet finished, but I know how to manipulate this derivative. There is yet another step that is involved here. I use the cyclic identity. Del P del T volume constant, del T del V pressure constant, del V del P temperature constant is minus 1. So always remember del P del T volume constant is equal to del V del T pressure constant, del V del P temperature constant. In both cases I divide by V. There is a minus sign in front. Sorry, we will not put the minus sign there, but rather we will put the minus sign here, because that's how we define the compressibility. So this is alpha P by kappa T. So therefore your entropy equation now becomes ds is Cv by T dt plus alpha P by kappa T. dV. So TdS is Cv dt plus alpha P over kappa T. Clearly, if I want to find out the change in entropy, if V is held constant but the temperature changes, then my change in entropy is del S del T volume constant, V is being held constant, dt. Correct? And the temperature doubles, which is essentially Cv by T dt. If I hold the temperature fixed and the volume, the information that is given to me, that the volume doubles, I want to find out the change in entropy. This is going to be del S del V temperature constant dV, which is alpha P over kappa T times dV. Right? du again here is del U del T. I'm looking at T and V. Volume, what did we do here? Yeah, okay. So del U del T volume held constant dt plus del U del V temperature held constant dV. Correct? So du is TdS minus PdV. So del U del T volume held constant is T del S del T volume held constant is the specific heat at constant volume. And del U del V temperature held constant is equal to T del S del V temperature held constant minus P. But we just now calculated del S del V, right? We calculated del S del V, temperature held constant, is equal to del P del T, volume held constant, and therefore this is equal to alpha P over kappa T, T times this minus P. Right. So if you put it over here, in fact you can get these relations always from the first law also. So if you put it over here, du is Cv dt plus del U del V, temperature constant, is T alpha P over kappa T minus P dV, because you know that TdS is du minus P plus P dV. So this becomes, here it becomes, just adds to this, but I should have somewhere a plus sign, because this is du is TdS minus P dV, which is equal to Cv dt plus alpha P over kappa T minus P dV. This T factor should not come anywhere, so one has to check. Right, so there has to be a T factor here. The T factor comes in when you're multiplying throughout by T, so this is correct, T alpha P kappa T minus P. So it is consistent. Just a remark, the way we have done this part, where we have calculated this and assumed that U as a function, here it assumes that U as a function of T and P in the earlier, so this is the example where we assume that S is a function of T and P, and then we went on to calculate U as a function of T and P. I just want to say that here I have essentially, I can do the same calculation, I can arrive at the same result from the first law, which is TdS is equal to du plus P dV, and du is TdS minus P dV. I have the expression for TdS which I have derived over here, but I don't have dV. This is dV, whereas what I'm interested in here is dP. So here then you do an additional step where you write down V as a function of T and P, and then you write down dV is del V del T pressure constant dt plus del V del P temperature constant dP, and you replace it over here and combine all of these expressions together. You are going to come up with the same expression. That perhaps would be one of the exercises. Right, the final one I want to discuss, and I want to discuss them very briefly, where I'm concerned about P and V, S as a function of P and V. Here, so again, ds is del S del P volume constant, dP plus del S del V pressure constant dV. So I have to now look at the structure of these relations. Del S del P volume constant. So then I'm looking for S and I'm looking for P, dV and dt. See, S always conjugates with T, therefore you should always have S dt and P dV, and dimension of energy, remember that, because your first law is the crucial thing here. S dt P dV, of course, the thing that comes to your mind is your free energy. Here you cannot have, I'm sorry, this cannot be P dV, then the derivative is with respect to volume, this has to be V dP. But we have seen that, right? Where did we see? When we looked at the Gibbs free energy. So del S del P temperature constant is del V del T pressure constant. Do I have, I cannot do this. So del S del P, now there is a volume which is constant here. So this is kind of a very strange derivative for which I cannot use any Maxwell's relation. So then I have del S del P volume constant, and I have to figure out how to do this. One possible way of trying it out is to del S del P volume constant, del P del V entropy constant, del V del S pressure constant is equal to -1. So you can relate del S del P with respect to del V del S. But here also you land up in trouble because this derivative is slightly strange. Why? Because you have del S, you're looking for a derivative which is del S del V pressure constant. So you cannot apply a Maxwell relation because you know your Maxwell relation must have, free corresponding free energy for which you want to derive such a relation will always have PdV. So S derivative with respect to volume is usually the variable which is conjugate to S that is held fixed. But it is something else which is held fixed. It is the pressure which is held fixed. So there is no easy way out for doing these things. So how to proceed with these two quantities? It might look very complicated things at first, but you see del S del P volume constant. This is equivalent to saying that I have del S del T volume constant, del T del V, del T del P volume constant. Similarly, del S del V pressure constant is actually del S del T pressure constant, del T del V pressure constant. Correct? This part is straightforward. Del S del T pressure constant is just Cp over T. Del T del V is 1 over, we can write down this as del V del T pressure constant, which is Cp over T alpha P, one of the response functions. But del P del T, so this one I can write down is del S del T volume constant is Cv over T, and this is del P del T volume constant. But look, I know what del P del T volume constant is. It's alpha P by kappa T. I can use this now. This is del P del T is alpha P over kappa T. So this is Cv over T 1 over alpha P kappa T. So ds is Cv over T kappa T over alpha P dV plus Cp over T alpha P dP, or this implies TdS is equal to Cv kappa T over alpha P dV plus Cp over alpha P dp, right? U as a function of P and V, one can still do the exercise. Here I have del U, del P, volume constant dP, plus del U, del V, pressure constant dV, and here I want to use again del U, del T, volume constant, del T, del P, volume constant is del U, del P, volume constant. So this one you know, this is CV. The other one is going to be del U, del T, pressure constant, and then you have del T, del V, pressure constant is equal to del U, del V, pressure constant. This is the one which is slightly more complicated, but we have already done that. We have done this is del U, del T, pressure constant. So del U, del T, pressure constant is, if you write down du as TdS minus PdV, then del U, del T, pressure constant. I think we did this before, right? Yeah, del U, del T, pressure constant is right over here. It is Cp minus Pv alpha P. So we can this is Cp minus Pv alpha P. And this one straightforward, I know this is going to be Cv del T del P volume constant is equal to del U del P volume constant, but del P del T we have again calculated here. We have again calculated del P del T volume constant as this, alpha P over kappa T. So Cv kappa T over alpha P is del U del P volume constant, and here this becomes, this relation now becomes del U del T pressure constant is Cp minus Pv alpha P times, there has to be a volume here, so volume del V del T pressure constant. So let's recast this slightly so that it is more easy to manipulate. Is V 1 by V is equal to del U del V pressure constant. This you know is alpha P. So this is Cp minus Pv alpha P divided by V alpha P is del U del V pressure constant. You can also calculate this relation from your first law, because you know TdS, you know this equation, and you also know du is TdS minus PdV, and then here you simply write V is equal to a function of that's fine, I don't have to write anything here because it's already a function of volume. So you will get the answers that you are looking for. Good. So now you know how to manipulate partial derivatives into calculating all these quantities, right? So please understand that in dealing with thermodynamic processes, pay attention to number one. What is the system? Number two, what information are given to you, which means, are you changing the coordinates or the volume? what are the coordinates, or let's say quantities, which are held fixed. So read the question or whatever information must carry this. Are you changing the coordinate or the volume? Which means, what are the physical quantities that are being changed? Are you changing the temperature? Are you changing the pressure? Are you changing the volume? And then again, what are the quantities which are held fixed? Is it an adiabatic process? Is the entropy is being kept fixed? Is it an isothermal process? Is the that means the temperature is kept fixed? Is it an isobaric process? That means the pressure is kept fixed. Is it an isocodic process? That means it's a volume which is kept fixed. So these information you must clearly find out. And the last point is, what has been asked? What do you seek? For example, do you seek the change in internal energy? Then you find out du is equal to, with respect to what? A derivative with respect to the quantity that is being changed. In the sense that you seek to find out how much the internal energy has changed if your temperature has doubled, keeping the volume fixed, or your pressure has halved, keeping the temperature fixed. So all these things, so you have to figure out what do you see, what has been asked. When you combine all these informations, then essentially everything now boils down to manipulating these partial derivatives, the ones that is going to come over here. And there, of course, you're going to use the three relations that we did. You're going to use this, we didn't have it here. You're going to use the cyclic relation, you're going to use the reciprocity relation, and you are going to use the chain rule of derivative. And on top of it, you're going to use the Maxwell's relations. And finally, the first law. All of this combined is going to give you the answer.